Hello students. So today I will teach you Rutherford alpha scattering experiment, mainly the derivation part. So many of the students approached me and they requested make a video on the derivation of differential scattering cross section, so related to Rutherford alpha scattering. So this will come in your BSc level or MSc level. A little bit difficult, the derivation is little bit difficult. You have to understand so few things to understand very clearly. Okay, so anyway you have the little bit idea about this terminology and all those things. I'm directly going to the derivation. So let's say here, so I'm starting from here. This is the I have written here scattering center. So scattering center means generally nucleus is the scattering center which is at rest. So alpha particles are approaching here like this. These are the alpha particles. So I have denoted the intensity of the alpha particles with I naught. So these alpha particles are approaching. Assume that the nucleus is fixed and it has a positively charged. So alpha particles are also positively charged and they will scatter in all the directions. As they are coming like this, they will scatter like this. They will scatter like this. They will scatter like this. Here also they scatter like this. Okay, fine. So now I am defining one quantity here, that is known as a solid angle. So solid angle is defined as a solid angle subtended by an area at a point. This is the area. So at this particular point, it subtends a solid angle. It is defined as area divided by r square. So as I have explained you in the class, when we use this spherical coordinates, it will comes out to be 2 pi sin phi d phi. So let me explain how it will be. So here, so the alpha particles are going like this. This is the direction of incident alpha particles. Of course they will not go like this, they will scatter in this direction. So this angle I define as the scattering angle. So it will happen in all the directions. It is a three-dimensional phenomena. So the particles which are scattered at an angle phi and d phi, so I have indicated here like this. It is a cone type. It is a cone type here. It is a cone type. It is a cone type. So this is the radius r, radius of the sphere. So if you are taking this strip, so this strip will have the radius opposite side. We can link with the sin phi. This is the r sin phi. So because I want to calculate this area, so thickness is 2 pi r sin phi. Thickness means total circumference, and r d phi. So this thickness. So length into thickness. So the length will come as 2 pi r, but r itself is r sin phi and thickness is r d phi. So arc length will be is equal to angle multiplied by radius type. Okay, fine. So that means, so these are the alpha particles which are incident here, like this, incident alpha particles. So they are scattered from this nucleus because nucleus will oppose that charged particles. It is also positive and this is also positive. Then is a repulsive force, and that to be central force type. So they will be scattered in this direction. So I call I naught is the intensity of the incident alpha particles, that is number of particles per unit time per unit area. So they will scatter in all directions. Let's add particular angle phi. So here I have defined the solid angle for you. The solid angle, remember here the solid angle is again a function of phi only, that is the scattering angle. So I have drawn a line. This I'm calling this axis, this is a symmetric axis. So this incident direction of alpha particles I am noting as a symmetric axis. So symmetric axis are, it is something like radial axis. So because the force involved here, the central force, it must have the symmetric about that axis. Okay, fine. So I hope it is clear. This point is necessary. This point is you have to remember this point. You have to understand also, because further, so when you go to the derivation part, these things are essential. Okay, fine. So let us come to here. So this diagram is already there even in our textbook also. So here I am taking, like this. So alpha particles are coming like this. They are incident from infinity, from far away. They are coming with a velocity v naught. So here it is a nucleus, it is a positively charged. Obviously they will not go like this, they will be repelled. So they will go in a curved path. Generally that curved path is known as the hyperbola path. So they are coming like this and they are deflected. So they are scattered, and this is the least distance of approach or closest approach. And the alpha particle will have the velocity v here. The velocity v is decreased, the kinetic energy is decreased. So now they scattered and they are going like this. This is the scattered direction. When again they reach to the infinity, they will have again velocity will be v naught. Of course, speed is v naught. So okay, so this will be the incident ray and this will be the scattered ray, and this angle I define as the scattering angle. Okay, fine. So I'll give you few terms here. So what is phi indicates, what is this path of this particle, and everything I'll write in a separate. Okay, all these things are required. So one more important point to be noted here, what is this p here. So let me explain here. So this is the line along which the alpha particle is supposed to come. If this nucleus is not there, this alpha particles are coming like this and they will go like this. Because of this nucleus, the alpha particles will not go like this and they will be reflected. They will be scattered. Okay, fine. So now this is the line along which the alpha particles are coming, incident direction. Now I will drop a perpendicular from nucleus to this line. That perpendicular, this is the perpendicular. That perpendicular distance is known as the impact parameter. So P is the impact parameter. Impact parameter. P is the impact parameter. So remember, impact parameter not necessarily 0. So when it is head-on type, it is 0. So head-on type in the sense, so here is the nucleus. So let's say charge will be Ze and it is fixed. So now for example, that charged particle, alpha particle is coming from infinity. So this is the alpha particle which has the charge 2e, which is coming from infinity. When it is coming from infinity, it has the velocity v naught. So when it comes here, the distance of closest approach may be here, let's say. After reaching here, its velocity will become 0. That means kinetic energy will become 0. So let us say this is the distance of closest approach. This is the distance of closest approach. So we can calculate this distance of closest approach by simply applying the mechanical energy conservation. So by applying the mechanical energy conservation. So when it is at infinity, it will have the kinetic energy. When it is here, when it is reached to the closest distance, head-on type, so it will become 0, then it will return its path like this. So it is coming like this. So kinetic energy becomes 0 here as it is decreasing, then it reverses its path. So at this particular point, so speed will become 0, decreasing kinetic energy will be is equal to work done by that repulsive force, that work done by that conservative force, that work done by conservative force simply. So the force is 1 by 4 pi epsilon naught Ze 2e divided by P. So you can call decrease in kinetic energy will convert into electrostatic potential energy. So from here we can calculate what is that B value, distance of closest approach for the head-on type. So that is Ze into 2e divided by 4 pi epsilon naught half m v naught square. This is the distance of closest approach. But I am not taking this case. So the alpha particle is not coming directly. So it is coming like this. So that means I can drop a perpendicular from here to here, that is P. So this is the special case where the P is 0. This is the special case where the impact parameter is 0. Head-on type. Okay. I hope this point is clear to you. As I said to you, I will give you a few terminology. So what is what here? So the path of that alpha particle, here I have shown you. So this alpha particle is coming like this and it is going. So it is coming like this and it is going like this. So what is this path? This path is the hyperbola. The trajectory of alpha particle in the field of nucleus. So I am writing here ACB, that is trajectory of alpha particle. Trajectory of alpha particle. So what is the trajectory of alpha particle? No doubt it is hyperbola. So you might have learned in your lower standard what is hyperbola. So okay, so this point it is required for us. So hyperbola, so you know this hyperbola will looks like this. So this will be the hyperbola. It is the hyperbola. So what is that equation of hyperbola? Something like x square by a square minus y square by b square is equal to 1 with eccentricity x square by a square. So with eccentricity E is equal to square root of 1 plus b square by a square. So we call a and b are the some major axis and minor axes. So let's see here. I am drawing a tangents at infinity. Generally we call as tangent at infinity are the asymptotes. So that asymptotes of these are the asymptotes of this hyperbola. So this is the intersection point. Call it as O is the intersection point. And there will be two foci. So one foci will be here, another foci will be here. At any one of the foci you can assume it is a nucleus. So here the alpha particles are coming like this with a velocity v0. So this is the asymptotes, means so like tangents at infinity. These are the tangents at infinity, asymptotes. Tangents at infinity, so known as asymptotes. So generally this length we consider as A, and this length from here to here we consider as A multiplied by E, AE. And of course this is A, and from here to here it is AE. Okay, so now the alpha particles are coming like this, and their nearest point will be the C, and let's say this is the nucleus here. So as these are the tangents, so I call this is the angle theta. So what is the slope of the tangent, or otherwise tangent at infinity? So tangent at infinity will have the equation tangent at infinity known as equation of asymptote. So that is simply y is equal to plus or minus b by a into x. So this is the slope. So here the slope b by a value will be the slope, that is equal to tan theta. That is the slope. So okay, fine. So then what is the impact parameter here? From the nucleus you drop a perpendicular. So I am dropping a perpendicular. So then this will become from the nucleus I am drawing a perpendicular on the asymptote. This will become the impact parameter. So this is I am dropping a perpendicular. So this will become the impact parameter. So we can correlate here. So theta and p. So I can apply for the sin theta. Sin theta will be opposite side divided by hypotenuse. So here if I relate, so sin theta will be is equal to, so this is the one point to be remembered. So before going to that, let us substitute in the eccentricity equation. So that eccentricity will become, so E will become square root of 1 plus b square by a square is tan square theta, b square by a square, 1 plus tan square theta. So 1 plus tan square theta b by a. So slope of the tangent we call generally b by a, that will be is equal to tan theta slope. So now if I substitute here 1 plus tan square theta, 1 plus tan square theta is very well known, that is sec square theta, that is equal to sec theta. So eccentricity in terms of that angle it will be sec theta. Okay, fine. So even we can relate this p and theta here. So how to relate that p and theta with this eccentricity? By if I apply for sin theta, so that sin theta will come out to be, sin theta will be opposite side divided by adjacent side. Opposite side will be p here, then adjacent side will be from here to here, that is AE. So you know these things from your 11th or 12th standard of conic section. So this is very well known. So just as it is diagram I am drawing here. So okay, so P by AE, from here I can go for E will be is equal to P by A, 1 by sin theta will be the cosec theta, 1 by sin theta will be the cosec theta. So I got the E value. Okay, so fine. So already here E value is there, here also E value is there. So from this both the E values I can conclude sec theta will be is equal to, so that sec theta will be is equal to P by A into cosec theta. So P by A into cosec theta. So you bring this P will be is equal to, or A will be is equal to sec theta you bring here. So from here A will be is equal to P. So it will comes out to be cos theta by sin theta, that is cos theta by sin theta will be is equal to cot theta. So P multiplied by cot theta. Okay, fine. So that means this angle is linked, this angle is linked with the eccentricity, that is E is equal to sec theta, that we have derived. So this is the basic like you required from your 11th or 12th standard conic section topic. Okay, I hope it is clear. So nothing great in this. So hyperbola idea we have taken. So further we require this hyperbola idea. So okay, fine. So one point is clear, ACB, that is the hyperbola. So what is the equation of hyperbola? That is something like x square by a square minus y square by b square with eccentricity we define. So tangent at infinity generally we call as asymptotes. So that asymptotes will have the equation. So y is equal to plus or minus b by x. B by a is the slope, y is equal to mx. Slope means tangent angle tan theta. So from there we have derived all these things. So with this point will be clear. So next point we will move to the next point. Okay, so the next point will be the phi. What is this phi? Will be the scattering angle. So phi is scattering angle. So phi is the scattering angle. So we can correlate that scattering angle and this angle theta. See here we can correlate. So you start from here. This is theta, this is phi, and this is theta. So all together theta plus phi plus theta. So 2 theta plus phi will become 180 degrees. So from here 2 theta will be is equal to 180 degrees minus phi. So from here theta will be is equal to pi by 2 minus phi by 2. So this is the relationship between them. So the scattering angle and the slope of the tangents can be linked here. So that means that link will be theta will be is equal to pi by 2, that is 90 degrees minus phi by 2. This relation also useful here. Okay, so fine here. So A is equal to P into cot theta, that means cot theta can be replaced with pi by 2 minus phi by 2. Okay, done. So next P will be the impact parameter that I have already explained to you. So impact parameter. So what is that impact parameter? So when I draw a perpendicular from nucleus to the path of incident alpha particles, this is the incident alpha particles are coming. So if I draw a perpendicular from here to here, that perpendicular length is known as the impact parameter. Okay, so impact parameter, the word you need to write very clearly. What is impact parameter? There you need to mention P means impact parameter. We need to understand that impact parameter. So because P zero case is different and P non-zero case is different, we are taking the generalized case, P non-zero case. So we can define like this. If we draw the same thing I am writing here, if we draw a perpendicular, in the direction of perpendicular on the direction of incident alpha particle from nucleus, then the length of that perpendicular, then the length of that perpendicular or this perpendicular is known as impact parameter. Is known as impact parameter. So I hope it is very clear to you what is an impact parameter. Okay, fine. So go to the next point to be. Okay, so the next one will be flux density of incident alpha particles. So I am writing for I naught. So this is the incident alpha particle. It indicates the number of alpha particles which are incident. So I naught. So I can write as number of alpha particles, number of alpha particles, so number of alpha particles crossing unit area per unit time normal to the direction of alpha particle beam, alpha particle beam. So this also called as flux density. This also called as flux density. So what is this? Number of alpha particles per unit time per unit area normal to the direction of alpha particle beam. So this is. So these are the alpha particles which are coming like this. I have indicated with I naught. So number of particles per unit time per unit area. Area means this is like a normal area, that is perpendicular like this. We need to keep like this. Okay, fine. So this is what I naught indicates. So let us define what is another quantity, so called I as a function of solid angle. I. It is also somewhat like intensity only, but intensity of the this relates to the incident on the nucleus, incident particle. This relate to the scatter. This relate to the scattered. So I define it. This will be like this: intensity of the scattered particles. Intensity of scattered particles, that is the number of particles scattered in the direction that is solid angle per unit solid angle per unit time. So remember here, this is I naught is the number of incident particles per unit time per unit area, but this is again intensity. Then again this is not incident, that is scattered, of course, scattered particles per unit time per unit solid angle. It is per unit time and per unit solid angle, I said you. So in the same, so when the particles are coming, these are the incident particles. So these are the particles incident here, alpha particles. So when they approach the scattering center, that is nucleus, they scatter in all the directions. So these are the scattered. So when viewed through some solid angle, of course solid angle is again a function of phi. So how many particles are coming per unit solid angle per unit time at that particular solid angle, or otherwise at that angle phi, scattering angle phi is defined as this quantity. Okay, clear? I hope it is. What is this? Now I want to define one of the important quantity here, so known as differential scattering cross section. Differential scattering cross section, d sigma by d omega. So d sigma by d omega. So this is known as differential scattering cross section. Differential scattering cross section. So what is this differential cross section? So this is very easy to understand. So let's say, for example, So alpha particles are coming like this. So when the alpha particles are coming like this, so there is a nuclear force will be there. Because of that nuclear force, they will be scattered in all the directions. Suppose, imagine that, so imagine that nucleus presents some area, nucleus will present some area to this alpha particles. It presents some, so this is the area, for example, it is presenting some area, this area. So this part of area of this part you can think of, or we can say it is an effective area presented by nucleus for the alpha particles. It is an effective area. Okay, so that effective area is important for me, so I am writing that. So that is, suppose or imagine that, so imagine that nucleus presents an area, so donate this will be some d sigma, area d sigma, perpendicular or normal, perpendicular to the path of the beam of alpha particles, such that whatever particle hit area d sigma are scattered into a solid angle d omega. So when the particles are coming and hitting, so when the particles are coming and hitting, so let's say there is a effective area something like this, effective area something like this. When the beam of alpha particles are coming like this, when the beam of alpha particles are coming like this, so when this beam of alpha particles are coming like this, the nucleus will present some effective area to this. So because of this, these alpha particles will scattered into certain angle, into a solid angle. So let us denote this solid angle will be like this. Okay, so imagine that nucleus presents an area d sigma, so there is an area, so that effective area that we need to calculate. Nucleus presents an effective area, so nucleus presents an effective area perpendicular to the path of the beam, such that whatever particle hit an area, so whatever the particle hits in this area, they are scattered into a solid angle. So that's why the definition of solid angle is important for us. Okay, so this area is d sigma and this is the solid angle, then the ratio this d sigma by d omega is called as the differential scattering cross section. Okay, done. So now we can see more about this differential scattering cross section here. So let us see this diagram. Let us see again this diagram. So number of particles which are crossing this area, the number of particles crossing this area. So what is this area? D sigma. So this area we can write total, this will be 2 pi r, that is 2 pi p, and thickness will be dp, thickness will be dp. So that means finally what is this represents? This quantity I naught multiplied by d sigma. What is I naught multiplied by d sigma represents? This I naught is a number per unit time per unit area multiplied by area. So that means number of particles, that is number of alpha particles, number of alpha particles. So number of alpha particles, they are like they are impinge or they are incident, number of alpha particles incident per unit time, number of alpha particles incident per unit time. So now the same number of particles, so here is the number of particles which are incident, the same number of particles will be scattered here, the same number of particles will be scattered here. Now let us denote what is this quantity represents. I as a function of solid angle, of course, into that solid angle. What is this I have written here? I means intensity, again the number of particles per unit time per unit solid angle, but we have already multiplying with the solid angle. So this can be the number of alpha particles which are incident, scattered, number of alpha particles scattered per unit time in that solid angle direction. So these are the incident particles and these are the scattered particles, of course. So the same number of, so suppose 100 particles per unit time incident, the same number of particles will be scattered. So we apply that particle number conserve, we have as the particle number is conserved, if these are the number of particles incident, the same number of particles has to scattered. Okay, so from here d sigma by d omega, that is I, that is intensity of the scattered divided by intensity of the incident. So this is known as the differential scattering cross section. Remember, differential scattering cross section. So can anybody guess what is the units here? What is this? Number per unit time per unit solid angle, number per unit time per unit solid angle. Okay, what is this? Number per unit time per unit area. So area by solid angle. So area is measured in meter square, solid angle is measured in steradians. So meter square by steradian will be the differential scattering cross section. So how to calculate the total cross section? Simple, integrate total cross section, it is the differential total cross section, simply sigma. So integrate this d sigma by d solid angle as a function of solid angle throughout the solid angle, integrate this solid, I'll get the total scattering cross section. Okay, so that means here it is I by I naught into total solid. So we know that already solid angle. So as it is the problem is of central force problem, this can be written as dA by r square, that is 2 pi sin phi d phi. So we know already expression for this. So we read the expression for this I by I naught. Okay, fine. I hope it is clear. So it's a terminology that once we know the terminology, we can easily understand rest of the things. Okay, fine. Okay, fine. So even some books will indicate this as sigma. So only simply sigma, differential scattering cross section, they will indicate simply with sigma. So as this force is the central force, it is only a function of this angle, I can write simply phi, sigma phi. Some people will indicate like this also, so not to be confused. So d sigma by d omega, so that is scattering cross section as a function of solid angle, but solid angle itself is a function of the scattering angle. Okay, some books will write like this also. Okay, so now we want to correlate between this differential scattering cross section and the impact parameter. So we need to correlate between the differential scattering cross section and the impact parameter. So we want to derive relation between relation between differential cross section and impact parameter P. So for that purpose, so just now we have written here, so this thing I naught into d sigma is this, the same thing I am writing here. So Here I naught into d sigma will be is equal to I omega into d omega. So we know this sigma, that is differential scattering cross section, can be by, it will be I divided by I naught. So that means I omega is equal to sigma as a function of phi into I naught. So what is d sigma here? Just now I said you what is this area will be. This area, incident alpha particles, this area will be 2 pi p dp. What is that solid angle will be? 2 pi sin phi d phi. Okay, so because of this area divided by r square, everything is here on length slide. So I'll substitute for this d sigma and I will substitute for this d omega. So now I naught into d sigma value, it is 2 pi p dp. This will be I naught into differential cross section. This solid angle will be 2 pi sin phi d phi. 2 pi sin phi d phi. So I want this sigma. So differential scattering cross section will be is equal to I naught cancel, 2 pi cancel. So here it is p is remaining. So you bring this side. I'll put some minus sign here. I'll explain you why I am putting p divided by sin phi, and here dp is there and there is a d pi. So dp divided by d phi. So the negative sign indicates that negative sign indicates p is impact parameter will decrease with phi. So negative sign is introduced. Negative sign is introduced because an increase of p will decrease phi. So that is dp by d phi will come as negative. So sigma phi is positive. Area cannot be negative. That's why we are putting that negative sign here. So I got the relation between sigma phi and p. Now we want p as a function of phi. So we want relation between. So now we want relation between p and phi. So how to get the relation between p and? So once I know the relation between p and phi, I can put here, I can get the sigma. So finding sigma is our total derivation. That's what you are facing the problem in deriving this. So we want the relation between p and phi. How to get the relation between p and phi? So very simple. So two ideas will be required here. One is conservation of angular momentum. So conservation of angular momentum. Another one will be conservation of mechanical energy. So one is conservation of angular momentum. Another one will be conservation of mechanical energy. So conservation of angular momentum. So when the particle will be at the initial state, initially it is far away. So conservation of angular momentum with respect to nucleus. With respect to nucleus it is far away with the perpendicular distance is p. So when it is coming like this, so here it is the nearest point. Here it is the nearest point. So let's say the distance from here to here, I'll take the nearest point distance, maybe d. The distance of closest approach. If you see the clearly what is d will be here. So O to C and O to N. So the distance d will be is equal to so N to O plus O to C. So from here to here it is A multiplied by E plus that is A, O to C, that is A. So there I have explained you in the hyperbola concept. So if you see this paper you can understand. So I want from here, this is the from here to here. From here to here it is AE and from here to here it is A. So that's why the distance d is equal to AE plus A. So the distance AE plus A is important because when it is here the perpendicular distance from the nucleus we require. AE plus A. So you can simplify that AE plus A. So the distance is coming as AE plus A. If I take A common, it will be 1 plus E. So but we already got A is equal to P cot theta. A is equal to P cot theta, E is equal to sin theta. So that means D is equal to, A value is P cot theta. So 1 plus E value is sec theta. E value is sec theta. So we have already derived. So if I simplify this, so D will be is equal to, so P cot theta, that is cos theta divided by sin theta into 1 plus cos theta, sec theta means 1 by cos theta. Okay, so if we simplify bit, so cos theta goes upward and it cancels with this, then D will be is equal to P. In the above it is 1 plus cos theta, in the below it will be simply sin theta. This is the relation between D and P. So D is equal to P into 1 plus cos theta by sin theta. Even if we can simplify further, we can simplify. If we required, we can simplify. So 1 plus cos theta can be written as 2 cos square theta by 2. 2 cos square theta by 2 whole divided by, so sin theta can be written as 2 sin theta by 2 cos theta by 2, half angle formulas. So cos cancel, so D will be is equal to, so sin theta, this formula, sin of 2 theta will be is equal to 2 sin theta cos theta. So that means sin of theta will be 2 sin theta into, so cos square theta will be is equal to 1 plus cos 2 theta by 2. So 2 I am bringing here. Okay. If that is the case, so 1 plus cos theta is 2 cos square theta by 2. Sin theta is 2 sin theta by 2 cos theta by 2. So what is after simplification I get here? Just simplify. D is equal to 2 cancel, cos cancel, 1 cos by 1 sin will be remaining. D is equal to P into cot of theta by 2. That is D is equal to cot of theta by 2. I hope it is clear. Just it is only trigonometry, nothing physics here. Okay, fine. So I got that distance also from here to here, the distance also. Here it is required, in my derivation it is required. So when I apply the conservation of angular momentum with respect to the nucleus, initial angular momentum, that is mv0 into perpendicular distance is P. The final it is mv into the distance is D. Just now we derived that D will be is equal to P cot theta by 2. That is P cot of theta by 2. So now energy conservation. When it is far away, assuming it has only kinetic energy, there is no potential energy. When it is the nearest point, it has the kinetic energy and also potential energy 1 by 4 pi epsilon naught q1, that is nucleus charge, q2 divided by separation D. Okay, so we know already, so when it is a head-on type impact, that B will be is equal to ZE into 2E divided by 4 pi epsilon naught D. 4 pi epsilon naught D. Okay. 4 pi epsilon naught into half m v naught square it is. We have already derived here in the first page itself. When the impact parameter is 0, then B will be is equal to like this, half m v naught square. So okay, so now it is simply the manipulation of all these things. So we need to solve for we need to eliminate V. From here V can be written as V naught P by D. So that means in place of V I can write V naught P by D. So if I manipulate this, if I simplify this instead of manipulation, if I simplify this, so when I simplify these two relations, what I get, that is important. So I write here what I get. So after simplification I get here after simplification of these two equations, after simplification, it is easy, I said you. So you just from here cancel, V will become V naught P by D. So in place of V naught P by D. In place of 1 by 4 pi epsilon naught ZE to E. So 1 by 4 pi epsilon naught ZE, half mv naught square B. So that time half mv naught square, half mv naught square, half mv naught square will cancel. Then what you will get here, P square will be is equal to D into D minus B. So this equation is very, very crucial for us. So I am leaving for you the simplification of these two equations. So you can solve it yourself. So now the heading itself, relation between P and phi. Relation between P and phi. So now move on to the next step. So I know here the D value, that is P cot theta, but substitute there. Substitute D value. So we have derived just now what is the D value. So here is the D value. So here is the D value we have derived. D value means when it is the nearest point, here is the nearest point. So this is the distance from here to here. This distance is already A. This distance is A multiplied by E eccentricity. We know already A value. We know already eccentricity value. So that means D value is equal to AE plus A. I did little bit manipulation and I got this P cot theta by 2. So now substitute here. So that means if I substitute here, what is that value I'll get? If I substitute there, that is P square is equal to D value is, that is P cot theta by 2. So D value P cot theta by 2 minus, remember here is a B value, it is B. Okay. So now take this inside, that is P square will be is equal to, so P square cot square theta by 2 minus B into P into cot of theta by 2. So you bring this side and this side, that is B multiplied by P into cot of theta by 2 will be is equal to, so P square into cot square theta by 2 minus 1. So 1 P will be cancelled, only 1 P is remaining. Cot square theta by 2 minus 1 can be written as, so you bring this cot theta by 2 here. So 1 P cancel. So only B is remaining here. So there is P, that is cot square theta by 2 minus 1 by, that is cot theta by 2. Cot square minus 1 divided by cot theta. So you can write in terms of sin u cos. So and you simplify this, you will get finally this entire thing after simplification, right? Cot, here it is cot theta will come, here it is 1 by cot theta tan theta will come. So cot theta by 2 minus tan theta by 2 will come. So cot theta by 2 minus tan theta by 2, B into cot theta by 2 minus tan theta by 2. So cot theta by 2 minus tan theta by 2, you write it is cos by sin, you write it is sin by cos, cross multiplied by, and all those things. After that I'll get simply B value as, so B will be is equal to 2P into cot theta. B value is equal to 2P into cot theta. So we require only P, that is P required. So P will be is equal to, from here B also I'll substitute, that value B also I'll substitute, here only I have written B value, I'll substitute here. Then what I'll get, the P value cot theta. Now it is the time to convert our theta in terms of phi. So theta in terms of phi, I have already explained to you what is the relationship between theta and phi. So here in this diagram, so the relation between theta is equal to pi by 2 minus phi by 2. I use here that theta will be is equal to 90 degrees minus pi by 2. So tan 90 minus phi theta will be is equal to So cot 90 minus theta, it will become tan. So that means, so from here I want p is equal to, so b divided by 2 tan of 5 by 2, tan of pi by 2. So from here I'll substitute the value of b. So b will equal to ze 2e 4 pi epsilon naught half mv square. So if I substitute there, then what I'll get the p value. So that p value will become ze square, that is cot of 5 by 2, we are writing 1 by tan as cot, divided by 2 pi epsilon naught mv naught square over, that is the p value. Okay, done. That is the p value. See, so I got the p value. Once I got the p value, here is in this paper we are searching for the scattering cross section. So in searching for the p, we searching for the p in terms of phi. So p and phi relation, this is what the p and phi relation. So finally we got the p and phi relation. So p is equal to ze square cot 5 by 2 2 pi epsilon naught mv square. Okay, fine. Next we substitute this p value there, then we'll get the answer. So finally, so differential scattering cross section sigma pi will be is equal to minus p into sin phi, so d by d phi of p, where we just now derived p will be is equal to ze square into cot of 5 by 2 divided by 2 pi epsilon naught mv naught square. Okay, fine. So now here this term is required, deep. So this term, so differentiation of this. So if I do the differentiation of this with respect to phi, so what is the cot differentiation? Cosec square. So d pi by dp will be equal to, so ze square by 2 pi epsilon naught mv naught square. Differentiation of that cot will be minus cosec square 5 by 2 by 2. Okay, fine. So now put back this here, and the p value is here. When I put that, so sigma differential cross section, sigma as a function of phi will become, then sigma as a function of phi will become, so the first term, that is p, don't forget the sin phi is there. So that is ze square. Anyway, this minus sign and this minus sign will become positive. No need to worry that negative sign. So that's why I substituted ze square, that is cot of 5 by 2 whole divided by 2 pi epsilon naught mv naught square. So and this is ze square divided by 2 pi epsilon naught mv naught square into cosec square 5 by 2 divided by 2, and don't forget this sin phi, that is 1 by sin phi. So that is sigma phi will be is equal to, if I rewrite, so cot 5 by 2, that means cos by, that is cos by sin, cot cosec square, that is 1 by sin square. Now I'll write this one thing, this sin phi can be written as 2 sin 5 by 2 cos 5 by 2 half angle. So 1 cos 5 by 2 cancels with this 1 cos 5 by 2, that means only by sin 5 by 2, 1 by sin square 5 by 2, 2 here and 1 here and 2 here, 3, and here it is sin 5 by 2, total 4. So that means in the z square 2 times will be there, ze square into ze square. So in the denominator 2 to 4, 4 to the 8, and this 2 will come as 16 pi epsilon naught 2 times is there, mv naught square 2 times is there, and 1 by sin power 4 5 by 2. Okay, from here 1, from here 2, from here 1, total 4. Okay, so z square e power 4, denominator 16 pi square epsilon naught square m square b naught power 4 sine power 4 5 by 2, or otherwise we can write like this: sigma differential scattering cross section will be is equal to z e square divided by 4 pi epsilon naught multiplied by, this is 2 times kinetic energy, and whole square. So 1 by sine we can write it as cosec power 4 5 by 2. So either way you can remember this. Okay, so this is what actually the finally formula we required. So people will struggle a lot, but the key equation, where is the key equation? Here is the key equation. I'll tell you, here is the key equation. So this is the important relation. This is the important relation. So that means relation between sigma pi and p. So that is coming from here, that is incident particles will be equal to scattered particles concept. So then we need to relate p and phi. For that the physics is involved here, conservation of angular momentum and conservation of mechanical energy. Then rest of the thing is your mathematics. Okay, so thank you students. So thank you. If you found any difficulty in deriving or in understanding anything, please post in my YouTube channel. Okay, thank you.